Now there are times when we need to integrate with respect to y. So if I were to take a function and revolve it around the y-axis, then I may need to be integrating with respect to y. So let's consider y equals x plus 1 on the interval 0 to 1, and I'm going to revolve this thing around the y-axis. Well, again, the very first thing I'm going to do is draw a picture from 0 to 1, so I really only need the upper half here. X plus 1, when x is 0, I'm at 1. And I'm going to 1 on the x-axis. That means I'm going to be up here. This will actually be at 2. And now I'm going to revolve this thing about the y-axis. Well, when I do, I get this sort of a thing. And there's my solid. So it's like this solid pipe with a cone thing dug out of it. So this area here is void, and this area here is all solid. Okay, so how are we going to integrate this thing? Well, first thing I want to do is, and also I want to run the y-axis here, I'm going to think of my radius, obviously, from the y-axis out to the function. But notice from 0 to 1, I have one situation, and then from 1 to 2, I have yet a different situation for my radius. So I'm going to break this down for, see, on 0, I guess I could do this as closed. 0 to 1, r of y is going to be equal to, well, what is this? That distance is nothing more than 1. And little r of y, the inner radius, well, there isn't one, so that must be 0. On 1 to 2, r of y, this outer radius, is going to be, well, it stayed 1. But this inner radius is now right here. See, this is r, this is r, this is little r. And what is that? Well, I need to figure that out. Let's see. I don't want an r there. What I want is y equals x plus 1. That implies x equals y minus 1. Therefore, little r of y equals y minus 1. So that's the function that's going to define small r. So my volume is going to be equal to, and I actually have two cases here. I'm literally breaking this up from 0 to 1, get the bottom half, which is all of this, and then 1 to 2, so I can get all of this. So the volume of this first piece down below is going to be the integral, well, actually pi, I'm sorry, pi times the integral, 0 to 1 of 1 squared, that's big R, minus 0 squared. Now, I'm writing this in here for completeness so you understand where it came from. I really don't expect you to put that 0 in there. If you get it, it's 0. Don't worry about it. I don't really expect you to square a 1. So if you just simply put 1 in there, you know, I get it. It's not a big deal. Plus, the second piece would be pi times the integral from 1 to 2 of 1 squared minus little r, which is y minus 1 squared dy. So this is obviously pi times the integral of dy plus pi times the integral of, from 1 to 2, I'm sorry, this is 0 to 1, of 1 minus y minus 1 squared dy. Now I could expand this, but I'm not going to, because I know if I do a U-substitution, if I let u equal y minus 1, then du is going to simply equal dy. So when I substitute back in, it's y minus 1. So I can integrate this without a U-substitution. I just know the way it's going to be. It's pretty obvious. So if I integrate this now, I'm going to end up with pi times y, evaluated from 0 to 1, which is going to be just pi, plus pi times, this is going to be y minus y minus 1 is squared, so it's be cubed over 3, evaluated from 1 to 2. So this piece right here is simply going to be, that was a really ugly arrow. There we go. Pi. This is going to be pi. Let's do it like this. Yeah, let me do it like this. I'm going to pull that pi out. Pi times 2 minus 1 is 1. 1 cube's a third. So 2 minus a third. Oops. A third. Oh, I need to fix that. A third minus 1 minus 0. So that's just 1. Put the 0 in. So what does that give me? I'm going to have pi plus pi times, so that pi and pi times 2 minus a third is 2/3 minus 1. Oops. 2 minus a third is not 2/3, excuse me. Let's get it together here. This is 6/3. This is 6/3 minus a third, so this would be 5/3 minus 1. So this is going to be pi plus, see, 5/3 minus 1. That's 5/3 minus 3/3. That's 2/3 pi. So this is actually going to be 5 pi over 3. So the volume of this whole thing, when I took this function and revolved it about the y-axis, is 5 pi over 3 cubic somethings, you know, whatever they happen to be, whatever the units I happen to be working in. Now, I could easily verify this using geometry, and we have several equations from geometry you may be familiar with, which incidentally, all of these are actually calculus results. In geometry and algebra, they're simply given to you as magical equations, but these are actually calculus results. Now, the volume of this is supposed to be right circular cylinder, not a tight one. It's a right circular cylinder, is pi r squared h. The volume of a right circular cone is pi r squared h over 3. That's important because what we had here in this diagram is a right circular cylinder, that is all of this, and a right circular cone, that's this piece right in here. So if I take the volume, the whole piece, pi r squared h, the right circular cylinder, and subtract from it the cone, I get the same thing that we were dealing with. So here I'm going to have pi, r is 1, and h, remember this came up to, where was it? I think it was 2, wasn't it? Yeah, that came up to 2. So h is 2. That's the volume of all of this, minus pi times r. R is going to be 1. The height is the height of this cone, which is also 1 over 3. So this is 2 pi minus, whoops, not minus, I'm sorry, minus, not equals, 2 pi minus pi over 3, which is 5 pi over 3 as previously advertised. So using what we know from geometry, some formulas from geometry, we can verify what we just did with all this integration.